Good evening, and welcome back to another episode of Sleeping with the Dinosaurs. Tonight, we journey back in time to meet a predator that has captured the human imagination for decades, the Velociraptor. You may think you know it from the movies, but the real creature was even more fascinating. Its story written not in Hollywood scripts, but in the shifting sands of a long-lost world. Before we begin our exploration, I'd like to ask you to gently tap the like button and subscribe so you can join us for more prehistoric journeys under the quiet cover of night. And in the spirit of connection across time and space, I'd love for you to leave a comment below telling us where in the world you are listening from this evening. Now settle in, slow your breathing, and let the darkness cradle you. Together we will slip into a place where the desert wind whispers through ancient dunes, and the rustle of feathers tells of a hunter moving under the moonlight. Our destination is 75 million years in the past, in a place the Velociraptor once called home. Close your eyes and step with me into a world that existed 75 million years ago. The air is dry here, so dry that your lips crack the moment the wind brushes past them. The sun, a molten disk high in the pale sky, pours down relentless heat, drawing mirages across the horizon. You stand on a dune of fine, tawny sand, not the desert as you know it today, but the desert of the Late Cretaceous. This place, which we now call the Gobi Desert, was already ancient when Velociraptor walked upon it. The land before you stretches wide and unbroken, a rolling sea of dunes that sway in form and shape as the wind sculpts their peaks and valleys. The sand itself is a living thing here, moving in ripples with the breath of the desert, sometimes whispering softly, sometimes hissing sharply as it lashes exposed rock. In the distance, stone ridges rise like the bones of the earth, eroded into strange shapes, towers, arches, and broken teeth, biting into the sky. Between these stone sentinels, narrow valleys provide shelter from the worst of the wind, and in these places life clings stubbornly to existence. Though this land may seem barren, life hums quietly all around. Sparse patches of vegetation grow in stubborn defiance of the arid climate. Hardy shrubs twist their roots deep into the earth to reach hidden pockets of moisture. Low, thorny plants stand like tiny fortresses against grazing mouths, and where underground water breaks the surface in rare oases, delicate ferns and cycads unfurl green fronds. Here, among the greenery, insects flit and buzz, their wing beats a faint, persistent hum beneath the hot breath of the wind. Small mammals with pointed snouts dart from cover to cover, their soft paws leaving fleeting impressions in the dust before the wind erases them. In the vast sky overhead, the world feels different still. The air is filled with the silent watch of pterosaurs, their leathery wings catching the rising thermals. They drift without a sound, eyes scanning for prey among the dunes and rocky outcrops. Occasionally, the sharp cry of a birdlike creature cuts the air, primitive avians that share this desert, flitting between the scant trees that cling to cliff edges. These trees, gnarled and weather-worn, stand as sentinels against time, their roots entwined in rock, holding on through centuries of harsh seasons. Across the sands you notice movement, a cluster of stout, beaked herbivores trudging toward the distant scent of water. They are protoceratops, no larger than sheep, yet armored with sturdy skulls and beak-shaped mouths perfect for cropping the sparse plants. They move as a group, their steps slow but deliberate, heads lifting now and then to scan for danger. Their presence draws other eyes as well, unseen eyes, hidden behind the curtain of wind-blown dust. The climate here is unyielding. The sun scorches the land by day, while the nights are cold enough to make breath plume in ghostly clouds. Rain is rare, arriving in sudden bursts that can transform the desert floor into a temporary garden. When storms come, they arrive with fury, black clouds spilling across the horizon, lightning splitting the sky, and rain that pelts the sand until it runs in rivulets. In those brief moments, the air smells rich and earthy, the scent of life returning, however briefly. Seeds hidden in the soil for months or even years respond quickly, sending green shoots toward the fleeting sun before the heat returns and the water is gone. But most days bring no such relief. More often, the weather turns violent in another way. Sandstorms. These rolling walls of dust can stretch for miles, blotting out the sun and swallowing the land in a choking darkness. Creatures caught in their path hunker down in crevices or bury themselves beneath the sand until the fury passes. In such a land, survival is not just about strength, it is about knowing when to move, when to hide, and when to strike. This is the world of the Velociraptor, sleek, agile, and sharply attuned to its surroundings. It was built for such conditions. Its long legs could carry it swiftly over the uneven terrain, and its stiff, counterbalancing tail allowed it to twist and turn without losing speed. The Velociraptor's eyes, large and forward-facing, were perfect for gauging distance and tracking movement even in low light. It could slip between rocky outcrops like a shadow, using the shifting sands and blinding winds to its advantage. At dusk, when the sun dipped low and the desert cooled, the Velociraptor came into its own. The light turned the dunes into waves of gold and crimson, and long shadows stretched across the land. Small creatures began to stir in the cooler air, emerging from burrows and rock shelters to forage. This was the time when danger was at its most patient. Somewhere among the rocks, a velociraptor would crouch low, its feathered body blending with the mottled colors of the land. The faintest sound, a rustle, a squeak, might draw its attention, its head tilting in quiet calculation. Feathers, delicate yet strong, would have ruffled slightly in the breeze, catching the last glimmers of fading sunlight. They were not the grand, sweeping feathers of flight, but fine plumes that insulated and perhaps signaled to others of its kind. In the quiet of this twilight, the velociraptor waited, not as a mindless predator, but as a creature finely tuned to every shift in its environment. This land was more than a backdrop to its life. It was a partner in its survival. The dunes offered cover, the ridges offered vantage points, and the sparse vegetation drew prey into predictable paths. The velociraptor's existence was one of constant adaptation, reading the land as if it were a book written in wind and sand. Every choice it made was a balance between risk and reward, a test that it faced each day and night. Even now, millions of years later, the echoes of this place remain. The Gobi still keeps its secrets beneath the sand. Here, fossilized bones and even traces of feathers lie preserved in the very ground where these animals once walked. In time, those bones would rise again, lifted into human hands, and their story would be told. But in the age we now walk into, there were no humans, no cameras, no museums. Only the endless desert, the creatures that called it home, and the silent march of deep time. And so, to truly understand the velociraptor, we must travel from this ancient landscape to the moment its story re-emerged in our own era, the day its bones were first pulled from the sands and shown to the modern world. The story of Velociraptor's discovery begins not in the deep past, but in the early decades of the 20th century, when the deserts of Central Asia were still as mysterious to science as the far side of the moon. At the time, paleontology was a discipline on the rise, filled with adventure, fierce rivalries, and the allure of uncharted fossil beds. It was in this age of discovery that an expedition would venture into the windswept expanse of the Gobi Desert and return with a find that would reshape our understanding of predatory dinosaurs forever. In the early 1920s, the American Museum of Natural History launched an ambitious series of expeditions to Mongolia. These journeys were led by Roy Chapman Andrews, a man whose exploits, complete with desert caravans, sudden sandstorms, and close calls with bandits, would later inspire adventure stories of their own. Andrews was a figure of almost cinematic presence, tall, confident, and unafraid of the hardships that came with exploring some of the most remote and inhospitable places on Earth. His team carried with them not only the tools of fossil hunting, chisels, picks, and plaster, but also the latest in scientific equipment, crates of supplies, and in true expedition fashion, an air of determined curiosity. The Gobi greeted them with the same extremes that Velociraptor had once known: blistering heat by day, bitter cold by night, and winds that could sweep away tents in a matter of moments. Camels bore the heavy loads across the dunes, and local guides led the way through labyrinthine canyons and over barren ridges. It was a place where the air felt timeless, as if nothing had changed in millions of years, and in truth, much of it had not. Beneath the sand, layer upon layer of sediment had locked away the bones of creatures long gone, preserving them with remarkable clarity. It was in one of these fossil-rich formations, the Flaming Cliffs, so named for the way the setting sun turned the sandstone a brilliant crimson, that a remarkable discovery was made. Among the weathered rock and shifting sands, the expedition uncovered a partial skeleton of a small, slender predator, unlike any they had seen before. Its skull was elongated and low, armed with a row of sharp, serrated teeth. Its arms were relatively long for a dinosaur, ending in three-fingered hands tipped with curved claws, and on the foot, even in fossilized form, was a blade-like claw, a sickle-shaped weapon that immediately caught the team's attention. The remains were incomplete, yet detailed enough to allow for a clear picture of this animal's predatory adaptations. The team named it Velociraptor mongoliensis, the name meaning swift thief from Mongolia. It was a fitting title, for the skeleton spoke of speed and agility, a hunter built for quick, decisive strikes rather than brute force. At the time of its discovery, Velociraptor challenged some of the prevailing assumptions about dinosaurs. In the early 20th century, the popular image of dinosaurs was still heavily influenced by the idea of slow, lumbering reptiles plodding through prehistoric swamps. Yet here was a dinosaur that was small, lightweight, and clearly built for active pursuit and precision hunting. Its skull shape and tooth structure suggested a diet of small to medium-sized prey, likely captured through speed and stealth. Its long, stiffened tail hinted at a life of constant movement, perhaps chasing nimble creatures across uneven terrain. What made this find even more significant was its context. The Flaming Cliffs yielded not just Velociraptor bones, but also the first dinosaur eggs ever discovered. This was a revelation. Until then, no one had ever found definitive proof that dinosaurs laid eggs. The Velociraptor's discovery, intertwined with this moment, became part of a broader picture of dinosaur biology that was only beginning to emerge. The early fossil record of Velociraptor was sparse, but it provided tantalizing clues. Over the decades, more specimens would be found, some in extraordinary conditions. These included skeletons preserved in dynamic poses, as if frozen in mid-action, and even fossils with impressions of quill knobs, tiny bumps on the forearm bones that indicated the presence of feathers. Such finds would later deepen the link between Velociraptor and modern birds, changing our view of dinosaurs as a whole. But in the 1920s, these connections had not yet been made. Instead, Velociraptor stood out as a unique predator, distinct from the larger carnivores like Tyrannosaurus rex that dominated popular imagination. It became a touchstone for the idea that not all dinosaurs were giants. Some were sleek, specialized, and adapted for quick, intelligent hunting. The very setting of its discovery added to its mystique. The Gobi Desert was a place few outsiders had seen, and its stark beauty became inseparable from the Velociraptor's identity. Images of its fossilized skull against the backdrop of the Flaming Cliffs found their way into scientific journals and popular magazines, sparking public fascination. It was not just the animal itself, but the romance of its unearthing, the idea of braving remote deserts to uncover the bones of an ancient predator that captured imaginations. Over the following decades, more Velociraptor remains would be unearthed, primarily in Mongolia and China, each new find adding detail to the picture. From these, paleontologists pieced together aspects of its anatomy, behavior, and evolutionary relationships. It became clear that Velociraptor belonged to a group of theropods known as dromaeosaurids, small to medium-sized predators with stiff tails, grasping hands, and the trademark sickle claw on the second toe. This group, in turn, was closely related to the ancestors of modern birds. Today, the significance of that first discovery is impossible to overstate. It was a window into a branch of the dinosaur family tree that was fast, agile, and feathered, a branch that against all odds survived the mass extinction 66 million years ago in the form of birds. And it was proof that even in the harshest of environments, life found ways to adapt and thrive. The Velociraptor's story, however, is far from complete. Fossils can tell us much, but they cannot show us the animal in motion, the way it ran, hunted, or interacted with others. To see that, we must turn from the moment of its discovery to the form it took in life, its size, shape, and the truth behind its appearance. When most people hear the word Velociraptor, their minds conjure an image born not from paleontology but from cinema. A towering, man-sized predator with scaly skin, long arms ending in hooked claws, and a mouth filled with dagger-like teeth. In popular films, it is fast, cunning, and lethal, and certainly terrifying when cornering a hapless human in some darkened corridor. Yet, as compelling as that image may be, the truth is far more fascinating, precisely because it reveals an animal perfectly shaped for the world in which it lived, rather than the one imagined for it on the silver screen. To understand the real Velociraptor, we must strip away the layers of fiction and meet the animal as it truly was, an agile, feathered predator roughly the size of a modern-day turkey. That comparison often surprises people, for we are so accustomed to envisioning dinosaurs as giants. Velociraptor, however, was a predator of modest proportions, on average about 6.5 feet from nose to tail, standing less than 2 feet tall at the hip, and weighing perhaps 30 to 40 pounds. Its proportions were elegant and purposeful. The head was long and narrow, shaped almost like that of a heron or other predatory bird, with a gently curved snout and large eye sockets that suggest sharp, forward-facing vision. Each jaw held a row of teeth, thin, serrated blades perfect for slicing through flesh. These teeth were not designed for crushing bone as in a tyrannosaur, but for cutting, indicating that Velociraptor likely relied on precision and repeated bites rather than a single overpowering blow to subdue its prey. The skull itself tells us much about its capabilities. Built lightly but reinforced in key places, it combined strength with speed of movement, allowing the raptor to snap its jaws quickly and with accuracy. Beneath the surface, muscle attachment points reveal a bite force suited for gripping and tearing, though far weaker than that of the massive apex predators of its day. This was not a brute force killer. It was a tactician, using its entire body in the hunt. Moving down the body, we find one of its most striking features, the arms. Each was relatively long, and ended in 3 slender fingers, tipped with sharp, recurved claws. These claws were more than just weapons. They were tools for holding struggling prey, climbing over obstacles, or even interacting with other members of its species. The joints of the arm allowed a surprising range of motion, enabling Velociraptor to reach forward or downward with precision. This, combined with strong grasping hands, would have made it adept at seizing small, agile animals that might otherwise slip away. Yet, the true hallmark of Velociraptor anatomy lay lower still, in its legs and feet. On each foot, the second toe bore a sickle-shaped claw, curved and razor-sharp, reaching more than 2.5 inches in length. This claw was held off the ground when the animal walked or ran, ensuring it remained sharp for when it was needed most. Muscles in the leg allowed the claw to snap downward with considerable force, potentially piercing flesh or pinning prey to the ground. Modern analogues such as the cassowary's fearsome inner claw offer some insight into its function, not necessarily to slash prey to pieces in a single motion, but as part of a coordinated attack involving the entire body. The legs themselves were long, slender, and built for speed. Bone structure suggests a creature capable of rapid bursts of movement, weaving between dunes or pursuing small prey over uneven terrain. The joints of the hip and knee provided both power and agility, while the long foot bones acted like natural springs, absorbing impact and propelling the animal forward. Velociraptor was not built to run endlessly like a cheetah over open plains. Instead, it was a sprinter and maneuverer, capable of sudden acceleration and rapid changes in direction. Supporting all of this was its tail, a marvel of natural engineering. While most people imagine a dinosaur's tail as a simple counterbalance, the Velociraptor's tail was something more, stiffened by bony rods called apophyses. It functioned like a balancing pole for a tightrope walker. This rigidity allowed the raptor to pivot sharply without losing stability, a crucial advantage in the kind of fast, twisting pursuit that would occur in the dunes and rocky gullies of its homeland. Fossil evidence suggests that while the tail was stiff, it was not entirely immobile. It could flex slightly, particularly near the base, offering both balance and subtle control. But perhaps the most surprising feature, and the one most often left out of fictional portrayals until recently, was the covering of feathers. While direct evidence of feathers on Velociraptor comes from later discoveries, such as fossilized forearms bearing quill knobs, their presence is now beyond doubt. These were not the large aerodynamic feathers needed for flight, but instead smaller plumes and pennaceous feathers that covered much of the body. They would have served multiple functions: insulation against cold desert nights, signaling to other raptors, and possibly aiding in maneuverability during high-speed chases. Imagine the Velociraptor in life, and the image transforms. No longer a scaly reptilian monster, but a sleek, bird-like predator with a body cloaked in a layer of soft, insulating feathers. Its plumage may have been mottled to blend with the sandy tones of its habitat: creams, browns, and ochres, perhaps with subtle striping or spotting. In the golden light of dawn or dusk, these feathers would have caught the sun in a faint sheen, giving the raptor an almost ghostly appearance as it moved silently through the dunes. Its movements would have been quick and deliberate, each step calculated, head swiveling to track the slightest sign of motion. The eyes, large, alert, and set forward for binocular vision, would have locked onto potential prey, judging distance with deadly accuracy. When the moment came to strike, its body could unleash a sudden burst of speed, tail stiffening, legs driving forward, claws poised for the final lunge. Scale in every sense is central to understanding the real Velociraptor. At 30 to 40 pounds, it was not a predator that could wrestle larger herbivores to the ground with sheer strength. Instead, it specialized in prey it could overpower quickly, perhaps small dinosaurs, reptiles, or mammals. Its size allowed it to move swiftly and stay hidden, striking from cover before vanishing again into the landscape. Even its brain size, while modest compared to mammals, was proportionally large for a dinosaur of its kind. This hints at a level of sensory processing and behavioral complexity beyond the slow, lumbering stereotypes of early paleontology. Its build was the sum of millions of years of evolutionary refinement, each limb, muscle, and bone serving a role in a life of precision hunting. This is the Velociraptor, as it truly was, not a giant monster, but a finely tuned predator, as perfectly adapted to its niche as any modern bird of prey. When we see it in this light, feathers ruffling in the wind, eyes bright with focus, body poised for action, we begin to understand that its power lay not in its size, but in the efficiency of its design. And while its form is striking in stillness, the real marvel is how that form came alive in motion. To see that, we must look more closely at the feature that has defined its reputation for decades: the curved claw on its foot, and the deadly precision with which it was used. For much of the 20th century, dinosaurs were imagined as great, leathery reptiles, their skin bare, their colors muted, their movements slow and deliberate. Feathers belonged to birds, and birds were thought to be an entirely separate branch of life. But in time, fossils began to tell a different story, one in which the boundary between bird and dinosaur blurred, and the Velociraptor stood as one of the clearest, most compelling examples of that connection. The first clue that Velociraptor was more than just a reptilian predator came not from its skin but from its bones. In the early 2000s, paleontologists studying a well-preserved Velociraptor forearm made a striking observation. Along the length of the ulna, the larger of the two forearm bones were a series of small, evenly spaced bumps. These bumps were quill knobs, the same kind seen in modern birds where strong feathers anchor to the bone via ligaments. They are not ornamental. They are structural, a physical sign that large, stiff feathers once extended from this part of the arm. The discovery was a turning point. Until then, feathers on dinosaurs had been confirmed mostly in smaller, earlier species from China, often preserved in fine-grained sediments that recorded even delicate filaments. Velociraptor's quill knobs meant that a larger, more advanced predator from the Late Cretaceous also bore feathers, not downy fluff but functional vanned feathers like those of a hawk or eagle. This revelation reshaped our mental image of the animal. Instead of a smooth-skinned, lizard-like creature, the Velociraptor would have been partially cloaked in plumage. The feathers may have extended along its arms, tail, and much of its body, providing insulation against the cold nights of the Gobi Desert. In some species of its close relatives, such as Microraptor, feathers were also present on the legs, though there is no direct evidence yet that Velociraptor shared that exact trait. But why would a flightless predator have such feathers? To answer that, we must think in terms of function. First, insulation. Deserts are known for their temperature extremes, and a coat of feathers would have trapped heat when the sun sank below the horizon. Second, display in the natural world. Feathers are often as much about communication as survival. The Velociraptor's feathers may have been patterned or coloured in ways that signalled to others, perhaps to attract mates, establish dominance, or coordinate with members of its kind. Third, manoeuvrability. While Velociraptor could not fly, its arm feathers might have helped stabilize it while running, or provided extra control during tight turns and leaps, much like the way modern birds of prey adjust their wings when pouncing. Feathers also tell us something profound about Velociraptor's place in evolutionary history. The structure of its skeleton, the wishbone, the arrangement of its hips, the hollow bones, all point to a close kinship with the ancestors of modern birds. In fact, when we look at the evolutionary tree, Velociraptor is a dromaeosaurid, a group of theropod dinosaurs that sits just outside the branch leading directly to birds. This means that Velociraptor was not a primitive dinosaur, but rather part of a specialized lineage that had already evolved many avian features. Consider its tail, long, stiff, and reinforced by bony rods. While it lacked feathers suitable for flight, fossil evidence from related species suggests that the tail may have been adorned with long feathers forming a fan-like structure. Such a tail could have served as a counterbalance in agile maneuvers, but also as a visual display. Think of a peacock's fan, but leaner, built for speed rather than courtship extravagance. Its arms, too, carry echoes of flight. Though incapable of generating lift, they were flexible and feathered, with shoulder joints allowing a degree of movement similar to that seen in modern raptors like hawks or falcons. Watching a Velociraptor in motion might have felt strangely familiar to anyone who has seen a bird of prey chase down quarry, wings partially spread to maintain balance and to make quick adjustments mid-pounce. One of the most remarkable implications of Velociraptor's feathers is what they reveal about the origins of flight itself. Feathers almost certainly evolved before flight, likely for insulation or display, and only later were co-opted for aerodynamic purposes in certain lineages. Velociraptor, though grounded, was wearing the legacy of this evolutionary story on its body, a reminder that flight was not a sudden innovation, but a gradual transformation over millions of years. If we could stand in the Gobi Desert of the Late Cretaceous and watch a Velociraptor approach, the feathers would change everything about how we perceived it. The sunlight would catch in the veins along its arms, perhaps revealing a subtle sheen of iridescence, much like the shifting colors seen in modern crows or magpies. The plumage along its neck might rise slightly in moments of alertness, the way a bird puffs up when threatened or excited. In cooler morning air, the feathers would lie flat, trapping warmth close to the skin, while in the heat of the day the raptor might lift them slightly to allow airflow and cooling. From a distance, its silhouette might even be mistaken for that of a large bird stalking through the dunes, until the head lowered, the eyes locked forward, and the sickle claw rose in anticipation of a strike. The connection to birds is more than superficial. Studies of Velociraptor's brain case suggest that it had a relatively large brain for its body size, particularly in regions associated with vision, balance, and coordination. This neural investment mirrors the sensory acuity seen in birds of prey today, where rapid processing of visual information is essential for capturing fast-moving prey. Its inner ear structure also hints at a keen sense of balance and spatial awareness, traits critical to both modern raptors and their prehistoric counterparts. Perhaps one of the most striking evolutionary clues comes from the very texture of its bones. Like birds, Velociraptor's bones were hollow, reducing weight without sacrificing strength. This lightweight construction not only allowed for faster, more efficient movement, but also suggests that the shift toward the avian body plan was well underway by the time Velociraptor roamed the Earth. It is easy to forget that Velociraptor was not an isolated oddity, but part of a broader evolutionary experiment playing out across the Cretaceous. All around the world, small to medium-sized feathered theropods were adapting to a variety of niches, some staying grounded hunters, others experimenting with gliding or full flight. Velociraptor, firmly in the grounded category, represents one of the most successful of these adaptations, perfectly suited to the harsh, open landscapes it called home. Its feathers, then, are more than just an adornment. They are a signature, a visible reminder of its place in a lineage that survived catastrophe and still soars in the skies above us today. Every crow, eagle, and hummingbird carries within its genes the echoes of creatures like Velociraptor, their feathers not merely a trait of flight, but an ancient inheritance. And so, when we speak of Velociraptor, we should picture it not as a scaled reptile, but as something closer to the ground-bound cousin of an eagle, sharp-eyed, quick-footed, feathers rippling in the wind as it stalks its prey. It is in this form, feathered and alive, that Velociraptor truly connects us to the deep evolutionary past. Yet as striking as its plumage was, perhaps nothing about Velociraptor is as infamous as the weapon it carried on its foot. A curved claw whose purpose has been debated for decades, and whose story we now turn to. If there is one feature that defines the Velociraptor in both science and popular culture, it is the claw, that long curved talon on the second toe of each foot. Even in fossilized form, it is unmistakable, a crescent of bone and keratin, its inner edge honed by nature into a blade-like curve. In life it would not have been dull or lifeless, but gleaming with a hardened sheath of keratin, the same material that makes up a bird's beak or a cat's claw. This was not an ordinary foot. It was a predator's toolkit, one of the most specialized weapons in the dinosaur world. When a Velociraptor walked, this claw did not touch the ground. The second toe was held cocked upward, the talon suspended above the dirt, sand, or stone so that it would remain sharp. The other toes bore the animal's weight, leaving behind three-toed footprints with one oddly absent, a ghost print where the killing claw should be. Even this detail tells us something about the raptor's way of life. It moved not just with speed, but with constant readiness, keeping its primary weapon prepared for the moment of need. The claw itself was proportionally large for the animal's size, averaging about 2.5 inches along its outer curve in life, not counting the keratin sheath that would have made it longer still. Its curve was deep, almost like a meat hook, designed to dig into flesh or hold a struggling creature in place. In modern animals, claws of similar shape often serve a grappling or piercing function rather than slashing. For example, the cassowary, a large flightless bird of Australia, bears an inner claw on each foot that it uses to kick with devastating force, often driving the point into an opponent or predator. For decades, paleontologists debated exactly how Velociraptor used its claw. The earliest ideas imagined it as a slashing weapon, delivering lethal cuts to the soft underbellies of prey. In the 1980s, this vision gained popular traction, painting the Velociraptor as a swift assassin leaping onto much larger dinosaurs and gutting them in dramatic fashion. But further biomechanical studies have suggested a more nuanced reality. The claw's curvature, combined with the flexibility of the second toe joint, seems better suited for gripping than slicing. Think of a climbing crampon or a grappling hook, something that latches on and doesn't easily let go. When this interpretation is combined with Velociraptor's strong legs and long arms, it suggests a predatory technique focused on pinning prey, perhaps holding it down with the claws while delivering repeated bites to vital areas. In this sense, the claw functioned much like the talons of a hawk or eagle, which use their feet to immobilize prey while their beaks do the killing. Supporting this idea are fossil discoveries such as the famous fighting dinosaurs specimen, in which a velociraptor is preserved in direct combat with a protoceratops. In this fossil, the raptor's sickle claw is embedded near the frill of its opponent, while the protoceratops's beak grips the velociraptor's arm. The moment is frozen in stone, a violent struggle between predator and prey, locked together in death, possibly buried suddenly by a collapsing sand dune or a desert storm. The position of the raptor's foot in this fossil has fueled the interpretation that the claw was used for stabbing or holding rather than sweeping cuts. Yet the claw may have served more than one purpose. Some researchers have proposed that it could have been used in climbing, either onto larger prey or even into trees or rocky ledges. While Velociraptor was not built for an arboreal lifestyle, the ability to scale short heights or cling to prey could have been advantageous. In the open landscapes of the Late Cretaceous, even a modest vertical leap might allow a raptor to get above its quarry, using gravity to its advantage in an attack. The muscular anatomy of the leg supports the idea of powerful, controlled strikes. The thigh bone, or femur, anchored large muscles that could pull the leg inward with force, while the tendons running down the shin to the toes were arranged for quick flexion. This combination meant the claw could snap downward in a fraction of a second, digging deep before the prey could react. Once embedded, the raptor could use its body weight to press down, increasing the grip. It is worth imagining what such a moment would have looked like in life. A velociraptor spots a small herbivorous dinosaur, perhaps a juvenile protoceratops, grazing near a patch of scrub. It crouches low, tail straight out for balance, feathers rippling in the dry breeze. Its steps are silent, the padded toes pressing gently into the sand. In a sudden burst, it closes the distance. 2, 3, 4 strides, and it is upon the prey. The raptor leaps, one foot extended, the curved claw poised like a hooked blade. Contact is made, the claw latches into the prey's side. The other foot finds purchase, and the raptor's arms wrap forward to grip tight. The prey struggles, but the claw holds fast, pulling the victim off balance. The velociraptor's jaws dart in, delivering quick, tearing bites until the fight is over. Such a hunting style requires precision and control more than brute strength. A failed strike would mean wasted energy and possible injury. The velociraptor's claw then was not a reckless weapon. It was a scalpel wielded with careful aim. There is also the question of how the claw functioned within the velociraptor's social and environmental context. If, as some evidence suggests, it hunted in coordination with others of its kind, perhaps not in the tightly choreographed packs of wolves, but in loose, opportunistic groups, the claw could have been used to pin prey, while another raptor moved in to assist. Alternatively, it may have been used in territorial disputes, with rivals grappling and slashing to establish dominance. In modern birds of prey, talons are also tools of intimidation. A raptor faced with a threat will often spread its wings and raise its claws in a display meant to deter the challenger without physical combat. It is possible that Velociraptor did the same, the raised sickle claws flashing as a warning before a confrontation escalated. In this way, the claw's presence could have prevented fights as often as it ended them. The claw's role in climbing remains speculative but intriguing. The stiffened tail, strong legs and gripping hands suggest that Velociraptor was agile in 3 dimensions, capable of scrambling over uneven terrain or pulling itself onto prey. In the complex landscapes of the Gobi Desert, which included rocky escarpments, collapsed dune faces, and sparse but climbable vegetation, such agility could have expanded its hunting opportunities. Ultimately, the sickle claw of Velociraptor is a symbol of specialization. It represents the culmination of millions of years of adaptation, honed for a style of predation that relied on speed, precision, and grip. Whether pinning a struggling prey animal, intimidating a rival, or climbing to gain an advantage, the claw was central to how Velociraptor interacted with its world. And yet, the claw was only one part of a larger predatory machine, a body and mind that worked in harmony to find, track, and capture prey. To understand the full picture of Velociraptor as a hunter, we must look beyond its weapons to the strategies and senses that made it so effective in its arid domain. To imagine how Velociraptor hunted is to imagine a life lived on the knife's edge between hunger and danger. In the late Cretaceous Gobi Desert, food was never guaranteed. The land was not rich with endless herds of giant prey, but instead scattered with smaller, quicker animals, each one alert, wary, and capable of turning predator into prey if the tables shifted. For a predator of Velociraptor's size, every hunt had to be calculated. A single mistake, a missed strike, a poorly chosen target could mean injury, and in this unforgiving environment, injury often meant death. The Velociraptor's build offers the first clues to its hunting style. It was not large enough to overpower the bigger herbivores of its time in direct combat. A Protoceratops in its prime would have outweighed it by several times, and even smaller ones had formidable beaks and muscular bodies. Instead, Velociraptor's long legs, stiff tail, and large eyes tell us it was built for bursts of speed, tight maneuvers, and precision attacks. This was a hunter that relied on stealth, surprise, and efficiency, not prolonged chases across open ground. Picture a typical hunt in the fading light of evening. The desert air cools, and shadows stretch long over the dunes. Velociraptor's feathers catch the breeze as it moves low and silent between scrubby plants, weaving through the landscape with practiced ease. Its large, forward-facing eyes scan the terrain, adjusting constantly for motion. The prey, perhaps a lizard basking on a rock, or a small mammal foraging for seeds, is unaware of the danger. The raptor's muscles coil with quiet anticipation. When the moment comes, there is no hesitation. A sudden burst of movement, a leap, and the sickle claw finds its mark. This style of hunting, short, explosive bursts from cover, is consistent with what we see in many modern predators of similar size. Bobcats, foxes, and owls all rely on ambush rather than pursuit, striking with speed and surprise before the prey can react. Velociraptor's combination of speed, agility, and precision claws fits neatly into this pattern. But what of the larger prey that it undoubtedly encountered? Fossil evidence suggests that Velociraptor did at times attack animals as large as itself, or even larger. The fighting dinosaurs fossil, showing a Velociraptor locked in combat with a Protoceratops, is the clearest example. In such cases, the attack may have been opportunistic, targeting a weakened, young, or distracted individual. A solitary Velociraptor likely could not take down a healthy adult Protoceratops without significant risk. But in the unpredictable theatre of survival, opportunities were sometimes worth the gamble. The question of whether Velociraptor hunted in groups remains unresolved, though it is tempting to imagine coordinated hunts. Some paleontologists point to the fossil evidence of multiple dromaeosaurids found in proximity to suggest group behavior, while others argue that such gatherings could be the result of scavenging rather than cooperative hunting. Modern analogues provide arguments on both sides. Lions hunt cooperatively, while most cats hunt alone. Harris's hawks work in groups, but many birds of prey are solitary. If Velociraptor did work with others, it was likely a loose and flexible arrangement, individuals drawn together temporarily by the availability of prey. The Velociraptor's keen senses played a critical role in its hunting. Its large eyes suggest acute vision, particularly in low light, meaning dawn and dusk may have been prime hunting times. The shape of its inner ear hints at an excellent sense of balance and spatial awareness, vital for chasing and pouncing in uneven terrain. Its sense of smell was probably respectable, if not as acute as a mammal's, allowing it to detect prey at close range or follow the scent of a recent kill. Dietary evidence for Velociraptor comes not only from studying its teeth, but also from direct fossil finds. One particularly telling specimen preserves the bones of a small pterosaur within the body cavity of a velociraptor, indicating it fed on flying reptiles when the opportunity arose. Another fossil shows Velociraptor remains alongside the bones of a protoceratops, further supporting the idea that it tackled prey near its own size. From these and other finds, paleontologists infer a diet that was varied and opportunistic: small dinosaurs, reptiles, birds, mammals, and even carrion when fresh kills were scarce. The teeth of Velociraptor were built for gripping and slicing, not crushing. This suggests that it would have taken multiple bites to subdue prey, tearing flesh in strips rather than breaking bones for marrow. Its feeding style may have resembled that of modern predatory birds, which use their talons to pin prey while tearing at it with their beaks. In Velociraptor's case, the sickle claw and grasping hands served as the anchors, while the jaws delivered rapid, shallow bites. Scavenging likely played a role in its survival as well. In a land where food could be scarce, turning away from a fresh carcass would have been wasteful. Its size made it small enough to feed on kills made by larger predators without drawing too much attention, yet big enough to defend itself from smaller scavengers. A dead protoceratops, a fallen pterosaur, or even a stranded fish in a drying pool could have provided a valuable meal. The hunting strategies of Velociraptor were undoubtedly shaped by the seasons. In wetter months, when plants flourished and herbivores were more active, prey would have been more abundant. During dry seasons, with food and water scarce, Velociraptor may have traveled farther, hunted more aggressively, or taken greater risks in targeting larger animals. Such seasonal rhythms are seen in modern predators living in arid environments, and there is no reason to think the ancient desert hunter behaved differently. It is also worth considering the role of intelligence in its hunting success. While Velociraptor's brain was not large by mammalian standards, it was relatively advanced for a dinosaur, especially in areas related to sensory processing and coordination. This may have allowed it to adjust its tactics mid-hunt, respond quickly to changes in prey behavior, and remember successful hunting grounds or patterns of prey movement. In a world where energy was precious and danger was ever present, efficiency was the Velociraptor's greatest weapon. Every movement had to count. Every hunt had to balance risk and reward. Whether stalking a small mammal in the twilight, snatching an unwary bird from the ground, or grappling with a struggling protoceratops, its body, senses, and mind worked together in the ancient choreography of predator and prey. Yet, even the most skilled hunter did not live by the hunt alone. To thrive, Velociraptor needed more than weapons and speed. It needed communication, awareness of others, and perhaps even a form of social interaction that shaped its life in ways beyond the hunt. And so, to see the whole animal, we must now step into the realm of how it may have lived and moved among its own kind. When we picture the Velociraptor, it's tempting to focus entirely on its physical form: the feathers, the claw, the sleek build made for speed. Yet to truly understand this predator, we must also step into the unseen realm of its mind and senses. For the Velociraptor was not simply a bundle of muscles and reflexes. It was a thinking, perceiving creature shaped by millions of years of evolution to read its world with precision. Paleontologists have long been fascinated by the relative intelligence of dromaeosaurids, the group to which Velociraptor belongs. In part, this comes down to something called the encephalization quotient, or EQ, a measure of brain size relative to body mass, often used as a rough indicator of cognitive ability. While dinosaurs as a whole had smaller brains than modern mammals of comparable size, some theropods, including dromaeosaurids, had EQ values that were noticeably higher than most of their kin. This suggests that Velociraptor possessed mental faculties above the dinosaurian average, potentially granting it greater adaptability, problem-solving ability, and behavioral complexity. Let us imagine a Velociraptor in the field, not hunting but observing, its head turned slowly, eyes scanning the dune ahead. The brain behind those eyes is processing streams of data. The pattern of shadows across the sand, the way a small patch of vegetation trembles in the wind, the faint glint of movement near a rock. In a fraction of a second, the Velociraptor is not only registering these details but evaluating them, deciding whether they are the stirrings of prey, the approach of a rival, or simply the idle dance of the desert wind. Vision was almost certainly one of its strongest senses. The position of Velociraptor's eyes on the front of the skull suggests a degree of binocular vision, the ability to overlap visual fields from both eyes, allowing for accurate depth perception. This is a trait shared by modern predatory birds such as eagles and owls, and it is invaluable for judging the distance to prey during a high-speed pursuit or a leap. Large eye sockets also indicate that its eyes themselves were sizable, meaning they could gather more light, a potential adaptation for hunting in low-light conditions at dawn, dusk, or even under moonlight. Color vision may have been part of its sensory arsenal as well, while direct fossil evidence for this is elusive. Many of Velociraptor's closest living relatives, birds and reptiles, have well-developed color vision. If Velociraptor shared this trait, it could have used it not only to spot camouflaged prey, but also to read the feather patterns of its own kind, potentially aiding in communication or mate selection. Imagine the subtle tilt of a head revealing the shimmer of iridescent feathers, understood by another raptor as a sign of health or readiness. Its sense of hearing, too, may have been acute. The structure of the inner ear in dromaeosaurids suggests they were capable of detecting a wide range of frequencies, possibly including higher-pitched sounds made by smaller prey animals. This sensitivity would have allowed Velociraptor to pick up the faint scurrying of a lizard beneath sand or the warning call of a bird hidden in scrub. Hearing would also have been essential for communication among members of its species, short calls, hisses, or growls that could carry through the shifting desert air without drawing the attention of larger predators. Smell, while perhaps not as developed as in some other predators, was still a useful tool. The olfactory bulbs of Velociraptor's brain were moderately sized, indicating a respectable sense of smell that could help locate carrion or follow the scent trails of prey. In a land where the wind could carry scents across long distances, this ability would have been valuable, though the Gobi's shifting sands could as easily scatter scents as preserve them. Beyond these physical senses, intelligence in Velociraptor may have expressed itself in behavioral flexibility. Fossil evidence shows that dromaeosaurids lived in a variety of environments, from forests to deserts, suggesting that they could adapt their hunting strategies to different terrains and prey types. This adaptability likely extended to individual behavior. One Velociraptor might favor ambushing from the cover of rocks, another might excel at chasing prey into a trap formed by dunes, and yet another might follow the edge of a Protoceratops herd, waiting for a young or injured member to lag behind. Such adaptability requires memory, not just short-term memory for tracking a moving animal, but longer-term memory for recognizing productive hunting grounds, seasonal migration patterns of prey, or the locations of water sources. This is where the Velociraptor's relatively large forebrain comes into play. While its mental world was not as rich as ours, it may have been complex enough to form simple mental maps of its territory, remember past encounters, and even learn from mistakes. Modern analogues help us imagine how such intelligence might have manifested. Corvids, such as ravens and crows, have small brains by mammalian standards, yet they solve puzzles, use tools, and recognize individual humans. Raptors like hawks and owls display remarkable patience and planning when hunting, often observing prey for extended periods before making a move. While we cannot know the exact mental capabilities of Velociraptor, these living examples remind us that small-brained does not necessarily mean simple-minded, especially when survival depends on strategy as much as on speed. It is also possible that intelligence played a role in social interaction. Even if Velociraptor did not hunt in coordinated packs, it likely encountered others of its kind frequently. In such cases, recognizing rivals, assessing dominance, and remembering the outcomes of past encounters could be crucial. A subordinate raptor might avoid conflict with a dominant individual it remembered losing to, while a victorious one might press its advantage in future interactions. These subtle social calculations require not just instinct, but memory and learning. The sensory world of Velociraptor was a dynamic one, layered with inputs from sight, sound, smell, and touch. Feathers, for example, were not only visual features but also tactile sensors, capable of detecting changes in airflow or the proximity of objects, much like the way a cat's whiskers help it navigate in darkness. Such sensory feedback could aid in everything from balancing during a leap to detecting the movement of nearby animals. Touch also played a role in hunting. The grip of its claws, both on the hands and feet, would have been informed by nerve-rich tissues capable of sensing pressure and movement, allowing Velociraptor to adjust its hold on struggling prey instantly. This fine motor control would have been essential in subduing animals quickly without wasting energy. When we combine all these traits, sharp vision, keen hearing, respectable smell, tactile sensitivity, and a brain capable of integrating them into split-second decisions, we begin to see Velociraptor not as a mindless killer, but as a calculated, adaptive predator. It was a creature that could read its environment, adjust its tactics, and perhaps even anticipate the actions of its prey. And yet, intelligence and sensory prowess alone do not paint the full picture. How these abilities shaped its interactions with others of its kind, whether in fleeting encounters, territorial disputes, or shared hunts, is a question that draws us inevitably into the next part of its story: the social behavior and communication of Velociraptor. The Velociraptor's claws, feathers, and senses tell us much about how it hunted and survived, but to see the whole animal, we must look at how it lived among its own kind. The fossil record, while silent on many details, offers subtle clues that, when combined with comparisons to modern animals, paint a picture of a predator whose life was shaped as much by interaction as by isolation. The Gobi Desert of the Late Cretaceous was not a crowded place. It was a patchwork of resources, oases, hunting grounds, sheltered nesting sites, scattered across a vast, unforgiving landscape. In such an environment, encounters between velociraptors may have been infrequent, but they were likely meaningful. Whether those meetings ended in cooperation, competition, or simple avoidance would have depended on the circumstances, the abundance of prey, the need to breed, or the defense of territory. The idea of Velociraptor as a pack hunter has long been a topic of fascination. In popular films, they are shown moving in highly coordinated groups, executing elaborate hunting strategies that rival those of wolves. The scientific evidence, however, is more ambiguous. Some fossil sites have yielded the remains of multiple dromaeosaurids together, leading to speculation about social hunting. Yet these could just as easily represent individuals drawn to the same carcass, succumbing together to harsh conditions or a sudden environmental disaster. If velociraptors did hunt together, it was likely in a loose and flexible fashion, perhaps small groups forming temporarily to take advantage of abundant prey, only to disperse once the opportunity passed. This is a pattern seen in many modern predators that are typically solitary, such as crocodiles gathering during fish runs or jackals pairing up to bring down larger animals. In such situations, cooperation is opportunistic rather than rigidly structured, requiring less complex social bonds than those of permanent packs. Still, even loose cooperation demands some level of communication. Here, Velociraptor's physical features offer tantalizing possibilities. Its feathers, for instance, could have carried visual signals. A raised crest of neck feathers, a flick of the tail plumage, or a quick spreading of the arm feathers could convey intention or mood, a warning to back off, a signal to advance, or a display meant to attract a mate. In modern birds, such signals can be subtle or dramatic, and they often function without sound, allowing for communication that does not alert prey or predators. Sound, too, would have been part of the velociraptor's repertoire. While we cannot know the exact calls it made, its close relatives among birds and other theropods suggest a range of vocalizations was possible. Hisses, growls, and low-frequency rumbles may have been used for intimidation or territorial defense, while softer chirps or clicks could serve in closer interactions between mates, siblings, or temporary hunting partners. Some sounds may have been low enough in pitch to travel through the ground as vibrations, a form of communication used by certain modern birds and reptiles to send signals over short distances without making themselves obvious to predators. Olfactory communication, though less glamorous, could have played a role as well. Scent marking is common in mammals, but reptiles and birds also use scent in more subtle ways. Feathers and skin oils can carry unique odors that may help individuals recognize one another. If velociraptors possess scent glands or simply carried distinct smells from their diet and environment, these could have provided information during close encounters, identifying kin, detecting reproductive status, or signaling territorial boundaries. Territoriality itself is another question. In resource-scarce environments like the Gobi, defending a rich hunting ground could mean the difference between survival and starvation. Yet defending territory also consumes energy and carries the risk of injury. A velociraptor might defend a particularly valuable area, a shaded water source, a nesting site, or a stretch of land rich in small prey, while remaining more tolerant of others in less critical areas. Such flexible territoriality is common among modern predators, from foxes to certain raptors, which patrol and defend only the areas most worth the effort. Conflict between velociraptors would not always have been a matter of life and death. Ritualized displays such as feather raising, tail lashing, or open-mouth threat postures could settle disputes without physical combat. If these warnings failed, a fight might involve quick, calculated strikes with the sickle claw, aimed more at driving the opponent away than causing fatal harm. Injuries, after all, were costly in a world without medicine. Survival favored those who avoided unnecessary risks. The breeding season likely brought its own set of social behaviors. While direct evidence is scarce, nesting sites of related species suggest that some dromaeosaurids may have guarded their nests and possibly even cared for their young. If Velociraptor shared this trait, males and females might have communicated through displays or calls during courtship, with the successful pairing leading to cooperative nesting efforts. The arrangement of eggs in carefully shaped ground nests, combined with the insulating and camouflaging properties of feathers, would have protected developing embryos from temperature extremes and predators. Parental care, if present, could have extended beyond the hatching stage. Modern birds of prey often feed their chicks for weeks, and some ground nesting birds lead their mobile young to food sources while keeping watch for danger. A velociraptor parent standing over its small, downy offspring might have used soft vocalizations or subtle movements of the tail to guide them, teaching the first lessons of stealth and awareness in a dangerous world. Juvenile velociraptors themselves may have formed temporary groups, both for safety and to practice hunting skills. Play behavior, chasing, pouncing, mock grappling, is seen in many intelligent predators and serves both to develop physical skills and to establish social ranking. While fossil evidence of play is all but impossible to confirm, the cognitive and physical capabilities of Velociraptor make it a plausible part of their behavioral repertoire. Not all social interactions would have been peaceful. In lean times, competition for food could turn deadly. A wounded or weakened individual might find itself harassed by others of its kind, driven away from a carcass or even attacked outright. Cannibalism, while unproven for Velociraptor, has been documented in other theropods and cannot be entirely ruled out. In such a harsh environment, survival sometimes meant making grim choices. Still, even if Velociraptor was not a highly social animal in the sense of wolves or primates, the ability to read and respond to the intentions of others would have been crucial. Recognizing when to fight, when to flee, and when to tolerate a neighbor could be the difference between life and death. This form of situational intelligence, rooted in observation, memory, and rapid decision-making, is a hallmark of many successful predators. In imagining the life of Velociraptor, it is important to strike a balance between the solitary image of a lone desert hunter and the overly romanticized pack hunter of fiction. The truth likely lay somewhere in between, an adaptable predator that could operate alone with skill, yet was capable of interacting, cooperating, or competing with others when circumstances allowed. And among those circumstances, None was more significant or more universal than reproduction, the cycle that shaped the rhythms of life for every creature in the late Cretaceous. To understand Velociraptor's story in full, we must now follow it from the moment of life's beginning, from egg to hatchling to adult hunter, and all the perils in between. Life for a velociraptor began in the most fragile of forms, a hard-shelled egg, no larger than that of a modern goose, lying nestled in a shallow depression in the sandy soil of the late Cretaceous Gobi Desert. In a world of heat and drought, where predators prowled and sandstorms could arrive without warning, every egg represented a gamble against the odds. Survival for the tiny life inside depended on protection, warmth, and the careful choices of the parents who placed it there. Though no complete velociraptor nests have yet been found, the nests of close relatives such as other dromaeosaurids and oviraptorids offer a window into what their arrangements might have been like. Eggs were often laid in circular patterns, sometimes in pairs, their pointed ends facing inward toward the center. This arrangement may have allowed a brooding parent to cover the clutch more evenly, regulating temperature through the heat of its feathered body. The environment would have posed constant challenges. Desert days could grow blisteringly hot, the sun baking the ground to temperatures that could kill developing embryos. Nights could turn sharply cold, leaching warmth from the sand. A vigilant parent, likely one of the adults, or perhaps both, would have needed to adjust constantly, shading the eggs in midday heat, settling down to cover them when the air cooled. Feathers in this stage of life were as important for protecting the next generation as they were for hunting. Hatching was the first great trial. After weeks of incubation, the chick within the egg would begin to break the shell from the inside, using a small temporary structure on its beak called an egg tooth. The process could take hours or even a full day. Outside the egg, the world was harsh and loud. The hiss of wind across dunes, the distant call of a pterosaur, the sudden patter of sand dislodged from a nearby slope. Inside the egg, the hatchling's heart beat fast, every movement a push toward life. When at last the eggshell split and the hatchling emerged, it would have been a fragile, down-covered creature, its eyes opening slowly to the bright light. Its legs and claws, though small, were already formed, ready to grasp and cling. In this first stage, the hatchling was utterly dependent on its parent for warmth, shelter, and food. Fossil evidence from related species suggests that dromaeosaurid parents may have brought small bits of food to their young or led them to safe foraging spots once they were mobile. Juvenile velociraptors likely grew quickly, as rapid growth is common among small to medium-sized theropods. This fast pace of development would have helped them reach a size less vulnerable to predators in as short a time as possible. Yet the months between hatching and independence were dangerous. Predators from other small theropods to mammals and even snakes would have seized any opportunity to snatch an unguarded chick. Even larger herbivores could pose a threat if they blundered through a nesting site. We can imagine a scene. The parent velociraptor stands guard near the nest, scanning the dunes. A sudden flicker of movement catches its eye, a small mammal creeping closer. The parent stiffens, tail held out for balance, and lets out a sharp, rasping call. The intruder freezes, then bolts as the raptor charges. The danger passes, and the parent returns to the nest, settling down so the young can press into the warmth of its feathers. As the juveniles grew, they would have begun shadowing the parent on short excursions, learning the fundamentals of life in the desert. They would practice stalking insects, chasing lizards, or pouncing on small prey under the watchful gaze of the adult. Play would have been more than simple amusement. It was training, honing the balance, speed, and accuracy they would need as hunters. By the time they reached half their adult size, the young velociraptors may have begun venturing farther afield, sometimes hunting alone, sometimes following the parent. These outings would have been times of both opportunity and risk. Every successful catch, even if it was only a small rodent or bird, reinforced their developing skills. Every close escape from a predator sharpened their instincts for survival. The transition from juvenile to adult was gradual, marked by changes in size, strength, and behavior. Feathers thickened, growing longer and more structured, providing better insulation and perhaps beginning to serve in display. The sickle claw, while present from early on, became more formidable as the leg muscles strengthened. The head elongated slightly, the teeth becoming more robust, better suited to tearing flesh. Adulthood likely brought with it a shift in priorities. A mature velociraptor would claim a hunting range, learn the seasonal patterns of prey, and perhaps seek out a mate during breeding season. For some, this may have meant returning to the same general territory year after year, especially if it offered reliable resources like water or shelter. The lifespan of a velociraptor remains uncertain, but estimates based on growth rates in related species suggest it may have lived for 10 to 15 years if it avoided injury or disease. In reality, few would have reached such an age. The dangers of predation, competition, and environmental extremes were ever present. A healed bite mark or broken bone in the fossil record is a silent testament to the hazards they faced. The cycle of life would have come full circle with reproduction. After mating, the female would find a suitable nesting site, somewhere with a balance of concealment and access to open space. She would prepare the shallow nest, perhaps lining it with vegetation or sand. Once the eggs were laid, the cycle began again. The long weeks of incubation, the careful defense against predators, the moment when the next generation cracked the shell and stepped into the ancient light. In this rhythm of birth, growth, and renewal, the Velociraptor's story mirrored that of countless other species before and since. It was a story written not just in bones and claws, but in the instinctive bonds between parent and young, in the shared knowledge passed from one generation to the next, through behavior rather than words. And yet, even the most careful life could be disrupted. The desert was not only home to the Velociraptor, it was a contested stage where many actors moved. To understand its full place in this ecosystem, we must turn to those it competed with, fought against, and sometimes fell to, the rivals and dangers that shaped its life from beginning to end. In the arid expanse of the Late Cretaceous Gobi Desert, Velociraptor was far from the only predator on the prowl. Life here was a constant negotiation between hunter and hunted, but also between hunter and hunter. Each day brought the potential for both opportunity and peril. To survive, Velociraptor needed not only to master its own craft, but also to navigate a landscape alive with competitors and threats. Perhaps its most iconic rival was the stocky, horn-faced Protoceratops. At first glance, the matchup might seem one-sided, a beaked herbivore versus a nimble predator. Yet the reality was far from simple. Protoceratops was no easy target. With a low, muscular body and powerful limbs, it could pivot quickly to face danger. Its beak was a formidable weapon, capable of delivering a crushing bite. In close combat, the herbivore's bulk and determination made it dangerous enough to wound or kill an overconfident velociraptor. Fossils like the famous fighting dinosaurs specimen capture the ferocity of these encounters, predator and prey locked together, each capable of ending the other's life. But not all rivals were prey. Other predators prowled the same hunting grounds, each with its own methods and preferred quarry. Oviraptorids, with their strong beaks, were adept at raiding nests and snapping up smaller animals. Though they may not have been direct competitors for the same prey as often, their overlapping territories meant disputes were inevitable. An oviraptor defending a nest might lash out at an approaching velociraptor, and the raptor in turn might harass or even prey on the young of its beaked cousin. Smaller theropods, too, shared the landscape. Some of these were close relatives. Other dromaeosaurids, whose appearance and hunting style were similar to Velociraptor's own. The presence of these kin could lead to competition for the same prey base. In times of scarcity, a carcass could become the center of a tense standoff, with each participant gauging whether to fight for possession or retreat to conserve energy. Then there were the larger carnivores. Tarbosaurus bataar, a massive tyrannosaur of the region, was a threat that no velociraptor could hope to match. Standing several meters tall and armed with a skull nearly as long as an adult human is tall, Tarbosaurus was the apex predator of its domain. To encounter one was not to engage, but to flee or hide. A velociraptor caught out in the open when a tyrannosaur appeared had few options, and any injury from such a predator would almost certainly be fatal. Even a carcass that might have provided a valuable meal could become a death trap if a Tarbosaurus arrived to claim it. The dangers weren't limited to other dinosaurs. The Gobi Desert teemed with smaller hazards, venomous snakes and lizards, mammals with sharp teeth and quick reflexes, and even large birds capable of snatching juveniles. Each represented a threat in its own right, particularly to young or weakened velociraptors. Environmental dangers were as relentless as living rivals. Sandstorms could descend without warning, their abrasive winds blinding eyes and clogging nostrils. The abrasive force could strip skin from bone and bury smaller creatures alive. A raptor caught far from shelter during such a storm would need to crouch low, head down, tail aligned with the wind, enduring the suffocating blast until it passed. The storms could also shift the very shape of the land, burying familiar landmarks and revealing new hazards or opportunities. Drought was another ever-present danger. When the sparse waterholes of the desert dried up, prey became scarce and competition more intense. Herbivores would range farther in search of food, thinning their numbers in any given area, and predators would be forced to follow. In such times, velociraptors might encounter unfamiliar rivals as territories shifted and overlapped. The stress of scarcity would make encounters more hostile, as each predator guarded any source of food with desperate intensity. Temperature extremes shaped behavior as much as competition did. Daytime heat could sap strength and speed, forcing velociraptors to seek shade or remain inactive during the hottest hours. At night, the cold could slow reflexes and stiffen muscles. The ability to adapt to these extremes, to know when to hunt, when to hide, and when to move on, was as important as any weapon or physical trait. Even illness and parasites played their role as silent dangers. Infected wounds from battles with rivals or prey could weaken a raptor, making it an easier target for other predators. Fleas, ticks, and mites would have been constant irritants, potentially carrying diseases that spread through populations. A weakened velociraptor might find itself unable to defend its territory, care for young, or even secure enough food to survive. The velociraptor's greatest defense against these threats was its adaptability. Its light build allowed for swift retreats. Its intelligence and acute senses helped it detect danger early. Its ability to switch between prey types from small reptiles to juvenile dinosaurs meant it could exploit different food sources as conditions changed. Still, adaptability had its limits. In a direct confrontation with a larger predator, escape was often the only viable option. This may explain why Velociraptor's body was built for maneuverability. The ability to weave through rocky terrain, slip behind dunes, or dart into crevices too small for a larger animal to follow. There may have been moments when danger became opportunity. A Tarbosaurus kill, left unattended even for a short time, could provide a feast. Scavenging carried risks. Returning to find the original killer reclaiming its prize was always possible, but the reward could be worth it. In such moments, the Velociraptor's caution and speed were invaluable. A quick dash to tear off a piece of meat, and an equally quick retreat could mean the difference between starvation and survival. For juvenile velociraptors, the list of dangers was even longer. Their small size made them vulnerable to almost every predator in the ecosystem, and even an aggressive display from a juvenile was unlikely to deter a determined attacker. Staying close to a parent or moving in groups may have offered some measure of safety, but independence brought exposure to the full range of threats. Those that survived their first year had already proven themselves capable of navigating a treacherous world. The balance of risk and reward in the velociraptor's life was constant. Every choice, to hunt, to fight, to approach a carcass, to enter another predator's territory, was weighed against the potential cost. Over millions of years, these pressures shaped a creature that was cautious yet bold when opportunity arose, capable of aggression but also quick to retreat when the odds turned. In this dangerous and competitive world, one of the most remarkable events in the Velociraptor's story occurred, a moment preserved in stone, capturing predator and prey in their final struggle. To understand the intensity of life and death in the Gobi Desert, we turn now to this extraordinary fossil, the fight frozen in time. There are moments in the fossil record so vivid that they feel less like the remnants of an ancient world and more like a photograph, a single instant of life captured forever in stone. Among the most famous of these is the extraordinary fighting dinosaurs fossil, a dramatic tableau that has come to symbolize both the ferocity of Velociraptor and the unforgiving nature of its desert home. The story of this fossil begins in 1971, when a joint Polish-Mongolian paleontological expedition was exploring the windswept flaming cliffs of the Gobi Desert. Here, layers of rich red sandstone had been sculpted by millions of years of wind and water, revealing glimpses of the creatures that once roamed this land. As the team moved across the cliffside, they uncovered something unlike anything they had ever seen. Two dinosaurs perfectly preserved in the midst of combat, their skeletons entwined in a death struggle that had lasted not seconds but 68 million years. One of them was a velociraptor, its familiar long, slender body twisted in motion. The other was a protoceratops, a stocky, four-legged herbivore with a large head frill and powerful beak. The velociraptor's curved sickle claw was embedded deep into the neck region of the protoceratops, a final lethal strike frozen in time. The protoceratops, for its part, had clamped its powerful beak around the raptor's right arm, breaking it in the struggle. Both animals were clearly locked in a fight to the death, a fight that ended abruptly, not because one overpowered the other, but because nature intervened. The prevailing theory is that the pair was caught in a sudden catastrophic event, perhaps a sand dune collapsing on top of them during the fight, or a flash flood of loose sediment burying them alive. The rapid entombment would have sealed them in an oxygen-poor environment, preventing scavengers and decay from destroying their final poses. Over millions of years, the sand turned to stone, preserving every bone, every joint, every telltale sign of their last moments. To stand before this fossil today is to witness the raw reality of predator-prey relationships in the Cretaceous. There is no cinematic exaggeration here, no staged drama, only the quiet truth of survival, where hunter and hunted sometimes perish together. The Velociraptor's position tells us it was attacking with precision, driving its sickle claw into a vulnerable area. The Protoceratops's bite shows that it fought back with equal determination, even as the predator closed in. This fossil is not just a striking image, it is a scientific treasure. It provides rare behavioral evidence, showing exactly how Velociraptor used its claw, not in a wide slashing motion, as once thought, but as a stabbing or gripping tool. The fact that the claw is lodged so deeply into the Protoceratops's neck supports the theory that velociraptors used it to immobilize prey while delivering repeated bites. The broken arm of the velociraptor also demonstrates the risks of attacking larger prey, reinforcing the idea that each hunt was a gamble. It also offers insight into the Protoceratops, an animal often overshadowed by flashier dinosaurs. Here we see its beak as a weapon capable of inflicting serious injury, and its sturdy build as an asset in fending off attackers. This was no passive victim. It was an adversary strong enough to meet the velociraptor's speed and agility with raw power. Beyond the anatomy, the fossil stirs questions about the circumstances leading up to this fatal encounter. Was the velociraptor hunting alone, or had it been part of a group singling out this particular Protoceratops? Was the Protoceratops healthy, or had it been weakened by injury or scarcity of food? Did the fight erupt suddenly, or was it the climax of a long pursuit through the dunes? These questions remain unanswered, but the fossil invites us to imagine the possibilities. The setting of the flaming cliffs adds another layer of significance. This area has yielded some of the most remarkable dinosaur fossils in the world, from nests of eggs to perfectly articulated skeletons. Its preservation quality speaks to the volatility of the ancient environment, a place where life could end in an instant under collapsing sand, leaving behind pristine records of behaviors otherwise lost to time. For paleontologists, the fighting dinosaurs fossil is a reminder of how rare such direct behavioral evidence is. Most fossils are scattered bones separated by scavengers, water, or the passage of time. To find two animals preserved in the act of interaction, especially combat, is extraordinary. It's the kind of find that transcends scientific circles, capturing the imagination of the public and reshaping how we think about these ancient creatures. In educational exhibits, this fossil has a unique power. Visitors are drawn to the immediacy of the scene. You can see the tension in the limbs, the determination in their locked positions. It transforms the idea of dinosaurs from abstract, distant creatures into living animals, driven by the same instincts for survival that shape life today. For many, it is the first time they truly understand that these were not monsters, but part of an ecosystem, predators, prey, and competitors, all bound in the same struggles as modern wildlife. The fossil also challenges the simplistic view of Velociraptor as an unstoppable killing machine. Here it is clear that even a skilled predator could face lethal resistance from its prey. The broken arm is evidence that the Protoceratops inflicted real damage before the fight was cut short. This reminder of vulnerability adds depth to our understanding of Velociraptor's life. It was dangerous, yes, but not invincible. In the years since its discovery, the fighting dinosaurs fossil has been studied, debated, and admired around the world. It remains one of the crown jewels of paleontology, a frozen story that bridges science and storytelling. For researchers, it is a wealth of anatomical and behavioral data. For the public, it is a moment of connection to a time when the desert was alive with the drama of survival. And perhaps most poignantly, it is a testament to the role of chance in the fossil record. Without the sudden collapse of sand, this fight would have ended like countless others, one survivor walking away, the other consumed by scavengers, leaving no trace for the future. Instead, it became immortal, a scene that allows us to stand across millions of years and witness the struggle as if it were happening before our eyes. Yet, this was just one encounter among thousands in the Velociraptor's life. Its existence was shaped not only by individual battles but by the larger patterns of movement and survival across its harsh homeland. To truly follow its story, we must now look beyond the single fight to the broader question of where and how it lived, the ranges it roamed, the territories it claimed, and the seasonal migrations that may have carried it across the shifting sands. The Velociraptor's life was not confined to a single dune or canyon. In the sprawling, unforgiving expanse of the Late Cretaceous Gobi Desert, survival meant knowing the land not just in one place, but across a shifting mosaic of habitats that changed with the seasons, the climate, and the endless movement of prey. Whether velociraptors roamed in wide seasonal circuits or maintained smaller, well-defended territories is a question still debated, but both scenarios would have demanded deep familiarity with the rhythms of their environment. The Gobi Desert of 75 million years ago was a land of extremes. Rainfall was scarce, but when it came, it could transform the land in a matter of hours. Shallow depressions became temporary lakes, grasses and ferns sprouted almost overnight, and the air filled with the calls of animals taking advantage of the sudden bounty. These bursts of abundance were followed, inevitably, by long stretches of heat and dryness, when waterholes shrank to muddy puddles and vegetation withered to brittle stalks. For the velociraptor, the key to survival was anticipating these changes and moving accordingly. If it held a permanent territory, that territory would have needed to contain a balance of resources: shelter from the desert's harsh winds, access to water during dry spells, and a range of prey animals sufficient to support the predator year-round. Maintaining such a territory would have required constant patrol. The velociraptor's sharp eyes would scan the horizon for intruders, its nostrils sampling the air for the scent of another raptor or a fresh kill. A tail flick, a feather display, or a threatening hiss might be enough to send a trespasser moving on. But when warnings failed, disputes could turn physical, short, violent clashes that decided who had the right to hunt and rest in a given stretch of land. Territorial boundaries were likely fluid rather than rigid lines. In times of plenty, when prey was abundant, overlapping ranges may have been tolerated with minimal conflict. But in lean seasons, boundaries would have tightened and competition intensified. A raptor defending a shrinking water source would have been far less forgiving of a rival than one hunting in a prey-rich oasis after the rains. The alternative to permanent territories was a more nomadic existence, with velociraptors following prey across the desert in seasonal migrations. Such movement might have been triggered by changes in prey behavior. Herbivorous dinosaurs like Protoceratops may have shifted their feeding grounds as vegetation patterns changed, while smaller mammals and reptiles moved in response to water availability. A velociraptor that could predict these shifts through memory, instinct, or observation would have had an advantage over one that stayed put in a dwindling food zone. Nomadic travel brought its own risks. Moving into unfamiliar areas meant encountering new competitors, predators, and terrain. It also required knowledge of safe routes, pathways between dunes and through rocky ridges that offered shelter from the blistering sun and from sudden storms. A migrating velociraptor might travel alone or in loose association with others moving in the same direction. Temporary alliances could form, especially if hunting conditions favored multiple predators working the same ground, but these relationships would dissolve as quickly as they formed when resources grew scarce again. Long-distance movement across the Gobi would have been dictated not only by prey, but also by the geography of the land. The desert was not a uniform sea of sand. It was broken by rocky outcrops, scattered oases, and ancient riverbeds. These natural features served as navigation points, water sources, and hunting grounds. A lone velociraptor traveling through the desert would pass from open dunes into the shadow of cliffs, through narrow wadis where the air was cooler, and into low-lying areas where rare greenery drew herds of grazing dinosaurs. Migration may also have been influenced by breeding cycles. If certain areas offered particularly good nesting sites, sheltered hollows, stable sandbanks, or ground with the right mix of firmness and drainage, velociraptors might have returned to them year after year. These seasonal movements, repeated across generations, could have formed predictable patterns in the life of the species. A young raptor, following a parent to a nesting site for the first time, might later retrace that same journey when it reached maturity. In defending territory or moving across it, the velociraptor's senses would have been constantly engaged. Its keen vision could spot movement at a distance, while its hearing picked up the calls of prey or the footfalls of a rival. Scents carried on the wind might reveal the presence of a fresh kill or the approach of a larger predator. These cues allowed the raptor to decide whether to press forward, change course, or lie low until danger passed. Water sources were focal points for both territoriality and migration. In a desert environment, a small pond or spring could draw animals from miles around, creating a concentrated hub of life and conflict. A velociraptor might wait in ambush near such a source, knowing that sooner or later prey would arrive, but so too would other predators, making such places risky. Approaching water required caution, and sometimes patience, circling downwind, moving slowly through cover, and striking only when the moment was right. Sandstorms posed an additional hazard during travel. A sudden wall of wind and dust could strip visibility to nothing, erase scent trails, and disorient even an experienced raptor. Those caught in the open would crouch low, turning their backs to the wind, tail wrapped around their bodies, feathers flattened tight. Others might seek the shelter of a rock face or a dune's leeward side, waiting hours for the air to clear. When the storm passed, the landscape could be unrecognizable. Familiar landmarks buried, new ones exposed, the ground reshaped by nature's hand. Velociraptors likely learned to read subtle signs of the desert's moods. The scent of moisture before a rain, the way prey animals moved before a storm, or the distant rumble of shifting dunes. Such awareness would have been essential for both stationary territory holders and nomadic travelers. The question of whether velociraptors engaged in long-distance cyclical migrations stayed mostly within defined territories remains unanswered, but the fossil record suggests they were capable of both strategies. The scattered nature of their remains across different fossil sites hints at a degree of mobility, while the structure of their claws, legs, and tails speaks to an agility suited to a variety of terrains. Whether defending a patch of desert or following the movement of prey across it, velociraptors were creatures in tune with their land. They knew where to find shade at midday, where the sand was firm enough to cross quickly, and where the wind carved gullies that could conceal an approach. Their survival depended on this knowledge, passed down not through spoken teaching, but through instinct and experience. But no matter how well they adapted to the rhythms of the land, the velociraptor, like every other species of its age, would eventually face a challenge it could not outrun. The closing chapters of the Cretaceous were marked by changes in climate, shifting ecosystems, and finally a cataclysm that swept nearly all dinosaurs from the Earth. To understand the end of Velociraptor's reign, we must look at the slow unraveling that preceded the final, sudden blow. For millions of years, the Velociraptor thrived in the arid landscapes of the Late Cretaceous, a master of stealth, agility, and precision hunting. But even the most perfectly adapted creatures are bound by the changing world around them, and as the final chapter of the Cretaceous period unfolded, the environment that had shaped the Velociraptor began to change in ways both subtle and dramatic. This was not an instant apocalypse, but a slow, creeping shift, the kind that begins as a whisper and ends as a roar. The Gobi Desert of 75 million years ago was already a challenging place to live. Its cycles of drought and brief abundance demanded resilience, adaptability, and constant awareness. For a predator like Velociraptor, survival hinged on the availability of prey, and prey in turn depended on the stability of vegetation and water sources. As climates began to shift in the waning days of the Cretaceous, these delicate chains began to fray. The first signs may have been seasonal patterns becoming less predictable. Rains might have come later, or in smaller amounts, leaving plants to wither sooner. Waterholes that once lasted into the dry season might have dried up weeks earlier, forcing herbivores to travel farther and more erratically in search of sustenance. For the Velociraptor, this meant that the rhythms it had learned and relied upon for generations were becoming unreliable. When prey became scarce, the competition between predators grew sharper. Rival velociraptors may have clashed more often over hunting grounds, and encounters with other carnivores would have been riskier. Opportunistic hunting strategies, taking juveniles of larger species, scavenging more often, stalking less traditional prey, may have become increasingly necessary. Such adaptations could sustain individuals for a while, but over time the entire ecosystem was straining under the changes. In addition to local shifts in the Gobi, there were broader, global changes unfolding. Geological evidence suggests that in the final million years of the Cretaceous, the world experienced fluctuations in temperature and sea levels. Massive volcanic activity in regions such as what is now India, the Deccan Traps, released vast amounts of gases into the atmosphere. This would have contributed to long-term climate stress, altering weather patterns, and possibly even triggering acid rain. While the Gobi was far from these volcanic fields, the effects of a changing global climate would not have respected distance. Dust from distant eruptions and changing wind patterns may have altered the composition of the air, affecting plant growth and the distribution of seeds. Fewer plants meant fewer herbivores, and the consequences would have rippled upward through the food chain, squeezing predators like Velociraptor between scarcity and competition. Despite these pressures, Velociraptor persisted. Its adaptability, keen senses, and opportunistic hunting style made it well suited to riding out hard times. It could hunt smaller, faster prey when larger animals were absent, and it could scavenge kills from bigger predators when fortune allowed. But adaptability can only go so far when the entire foundation of an ecosystem is eroding. Then came the event that would end the age of dinosaurs entirely, sudden, catastrophic, and global. Roughly 66 million years ago, a massive asteroid struck what is now the Yucatan Peninsula in Mexico. The impact released more energy than billions of atomic bombs, sending shockwaves across the planet. The immediate devastation, tsunamis, wildfires, earthquakes, was far from the Gobi Desert, but the aftermath reached every corner of the Earth. In the weeks and months that followed, dust and debris thrown high into the atmosphere blocked sunlight, plunging the world into a long, cold darkness. Photosynthesis slowed or ceased entirely, plants died, and the herbivores that depended on them starved. The predators in turn faced the collapse of their food sources. For Velociraptor, already living on the knife edge of survival in a harsh desert, the loss of prey was catastrophic. The cold would have been especially brutal in the Gobi's already extreme climate. While Velociraptor's feathers may have provided some insulation, they could not counteract the sustained drop in temperatures or the scarcity of food. Even scavenging became difficult when so many animals were dying at once. In this darkened world, the delicate balance of predator and prey unraveled entirely. Juvenile velociraptors, unable to compete for scarce resources, would have been the first to perish. Adults weakened, their strength eroded by hunger, becoming vulnerable to injury and unable to defend themselves or their territories. The once vibrant landscapes of the Gobi grew silent, the calls of birds and the rustle of prey replaced by the whisper of wind across empty dunes. The extinction was not instantaneous. For months, perhaps even years, scattered survivors may have clung to life in isolated pockets where food remained, but the interconnected web of life that had sustained them for millions of years was gone. Eventually, even the last of the velociraptors succumbed, not because they had failed to adapt in ordinary times, but because the scale of the catastrophe left no room for survival. Yet, in a sense, Velociraptor's lineage did not end. The evolutionary branch to which it belonged was deeply intertwined with the ancestry of modern birds. While Velociraptor itself vanished, its distant cousins, small feathered theropods better suited to surviving on seeds, insects, and other modest resources endured. From those survivors, the avian world we know today eventually emerged. Every hawk that scans a field, every crow that cocks its head in thought, carries a whisper of the velociraptor's legacy in its bones, feathers, and instincts. For the Gobi Desert, time erased the scars of the extinction. The dunes shifted, the cliffs weathered, and the skeletons of those last velociraptors were buried deeper in the sand. Millions of years later, paleontologists would uncover their remains, piecing together the story not just of their life, but of their final days. These fossils, silent yet eloquent, tell of a predator that once ruled its niche with unmatched skill, only to vanish in the face of forces far beyond its control. In the shadow of extinction, Velociraptor's life takes on a new dimension. It was not merely a hunter defined by its sickle claw and sharp mind, but also a survivor shaped by environmental pressures until the very end. The story of its disappearance is not one of failure, but of the profound vulnerability shared by all life in the face of planetary change. And while its reign ended, its image and legacy have endured, a legacy that would be transformed in ways even the most observant velociraptor could never have anticipated. To understand that transformation, we must step forward from the prehistoric sands into the modern world, where Velociraptor's name and likeness have taken on a life of their own in human culture. Few dinosaurs have achieved the pop culture immortality of Velociraptor. To much of the public, its name conjures the image of a human-sized, scaly-skinned predator, sleek, fast, and cunning, stalking its prey through darkened corridors or tall jungle grass. This is the Velociraptor of blockbuster films and best-selling novels, a creature as much a product of imagination as of science. It is also, in many ways, a character wearing the mask of a different dinosaur entirely. The modern image of Velociraptor in popular culture owes much to its starring role in a certain globally famous movie franchise. In these films, raptors are portrayed as towering over their human co-stars, standing roughly the height of an adult man, with narrow crocodilian snouts and a habit of communicating in complex vocal calls. They are shown opening doors, outsmarting their prey, and moving in perfectly coordinated packs. The effect is terrifying and undeniably captivating, but it is also, from a paleontological perspective, riddled with inaccuracies. The first and perhaps most glaring misconception is size. The real Velociraptor was not man-sized but closer in stature to a large turkey. It measured about 2 meters from snout to tail tip, but most of that length came from its tail. Standing at the hip, it reached only about half a meter tall, not quite knee height to a human. It was light too, weighing roughly 15 kilograms on average. In the films, much of the visual inspiration came from a related but much larger dromaeosaurid called Deinonychus antiropus, which lived in North America some 50 million years earlier. The decision to use the name Velociraptor rather than Deinonychus was creative rather than scientific, chosen for its sharper, more memorable sound. Another common misconception concerns appearance. For decades, the general public pictured all dinosaurs as scaled reptiles. Early fossil reconstructions reflected this bias, and even after scientists found clear evidence of feathers in dromaeosaurids, the featherless image persisted in much of the media. The real Velociraptor was feathered, likely with arm feathers strong enough to form a partial wing and a tail plume that could have been used for balance and display. Its skin was not bare and leathery, but cloaked in plumage that would have given it a distinctly bird-like appearance. The portrayal of velociraptors as hyper-intelligent is another area where reality and fiction diverge. While their relative brain size suggests they were more intelligent than many other dinosaurs, and possibly capable of problem-solving behaviors, they were not on par with chimpanzees or dolphins. Their intelligence was probably closer to that of modern birds of prey, enough for adaptable hunting strategies and keen awareness, but not for the kind of elaborate human-like reasoning seen on screen. The movie raptor's ability to coordinate pack hunts with military precision is speculative at best. Cooperative hunting in velociraptors has not been conclusively proven, and if it occurred, it was likely less organized and more opportunistic than depicted. Speed is another exaggerated trait. In films, velociraptors are shown sprinting at extreme speeds for long distances, easily overtaking human prey. While the real animal was certainly fast for its size, biomechanical studies suggest it was built more for agility than for extended high-speed chases. Its long legs and stiffened tail would have allowed for quick bursts of movement and sharp turns, perfect for ambushing prey in cluttered environments, but it was unlikely to sustain top speed over long stretches. The sickle claw, however, is one detail that films get partially right, at least in emphasizing its importance. The hooked talon on the second toe of each foot was indeed a primary weapon, but the slashing attacks seen on screen are not fully supported by the fossil evidence. Modern research suggests the claw may have been more effective as a stabbing or pinning tool, used to hold prey in place while the jaws delivered repeated bites. The differences between the real velociraptor and its cinematic counterpart are significant, but they do not diminish the animal's appeal. In fact, the truth arguably makes it even more fascinating. Knowing that such a small, feathered predator could be so efficient and adaptable in its harsh desert habitat highlights a kind of quiet, enduring power that needs no Hollywood embellishment. Still, the pop culture version has left a deep mark. Museum visitors often arrive expecting to see the towering, scale-covered raptors of the movies, and are surprised to find that the fossil skeletons are far smaller. This has led to challenges and opportunities for educators. On one hand, it can be difficult to correct deeply ingrained misconceptions. On the other, the gap between myth and reality offers a chance to engage people's curiosity, to explain how scientific understanding changes over time, and how paleontology often reveals stories more interesting than fiction. Velociraptor's fame has also boosted interest in paleontology as a whole. Many professional scientists today trace their fascination with dinosaurs back to those larger-than-life portrayals, even if the details were inaccurate. In this way, pop culture's version of Velociraptor has served as a gateway, the hook that draws people in, leading them to discover the real science behind the legend. Beyond film, Velociraptor appears in books, video games, comic strips, toys, and countless internet memes. It has been reimagined in nearly every conceivable form, sometimes realistic, sometimes fantastical, sometimes comedic. Velociraptor, a popular meme featuring a raptor deep in thought, plays on the cultural image of Velociraptor as both dangerous and intelligent. In children's toys, it is often depicted without feathers, reflecting older ideas, while newer educational models increasingly add accurate plumage. Artistic depictions of Velociraptor have evolved alongside scientific discoveries. Early reconstructions in the mid-20th century showed it as a sluggish, lizard-like creature. By the 1980s, influenced by the dinosaur renaissance in paleontology, it was portrayed as an active, agile predator, a shift that directly influenced its pop culture rise. Today, paleo art often emphasizes its bird-like qualities, from the arrangement of its feathers to the alert, forward-focused gaze of its eyes. The persistence of inaccuracies in popular media is a reminder of the inertia of cultural images. Once an image takes root, especially one as dramatic as a human-sized, scaly super predator, it can be hard to dislodge. Filmmakers and game designers sometimes choose to maintain the older, less accurate version because it is more familiar to audiences, or because it better serves the needs of the story they want to tell. For scientists, the goal is not to strip away the wonder inspired by pop culture's Velociraptor, but to redirect it toward the real creature, to show that the truth is equally compelling. The actual Velociraptor was a small, feathered hunter perfectly adapted to its niche, with keen senses, agile movements, and a lineage that stretches forward into the birds we see today. This is not a demotion, but a transformation from a monster of fiction to an animal of extraordinary reality. The journey from the deserts of Mongolia to the screens and imaginations of millions is a remarkable one. Velociraptor has transcended its own extinction to become an enduring symbol, a shorthand for speed, cunning, and predatory skill. And in doing so, it has ensured that its name, at least, will not be forgotten. But the real legacy of Velociraptor lies not in its pop culture fame, but in the fact that its story did not truly end with the extinction event. Its evolutionary line continues, soaring and stalking in skies across the world. To close our journey, we must follow that thread from the fossil beds of the Gobi into the modern age, where the Velociraptor's living relatives still carry its ancient heritage. Though the Velociraptor itself vanished in the mass extinction that closed the Cretaceous period, its story did not end. The animal we know from the fossil record is part of a much larger narrative, one that stretches back tens of millions of years before it lived, and forward all the way into the present day. To understand this legacy, we must follow the thread of its lineage through time, watching as its traits and adaptations passed on, transformed, and ultimately found new life in the birds we see today. The link between Velociraptor and birds was once a controversial idea. For much of the 20th century, dinosaurs and birds were thought to be distant relatives, connected only in the deep past through some generalized reptilian ancestry. But discoveries from the 1970s onward began to rewrite that understanding. Feathers preserved in fine-grained fossil beds in China revealed that many small theropods, the group of dinosaurs to which Velociraptor belongs, had plumage strikingly similar to that of modern birds. Anatomical comparisons, too, showed uncanny similarities: wishbones, furculae for muscle attachment, hollow bones for lightness, and limb proportions designed for balance and agility. Velociraptor was part of the dromaeosaurid family, a branch of theropods that also includes other well-known feathered predators, such as Deinonychus and Microraptor. These animals were not evolutionary dead ends, but rather close cousins of the direct ancestors of modern birds. Their bodies already bore many avian hallmarks: the three-fingered hand, the swiveling wrist joint that allowed wing-like movement, the long feathered tail for stability, and even the quill knobs on the forearm bones where flight feathers would have anchored. From an evolutionary standpoint, Velociraptor sits just outside the direct avian line, close enough to share most of the key features, but adapted for a ground-based predatory lifestyle rather than flight. If we could watch its movements, we might be reminded of a stalking bird of prey, wings held slightly open for balance, head tilting with sharp, calculated motions, the tail adjusting subtly to shifts in direction. The sickle claw, so iconic to Velociraptor, finds its distant echo in the talons of modern raptors. Like the ancient predator, these birds use their claws not for casual scratching, but as precision instruments of hunting, gripping and pinning prey before delivering a killing bite or beak strike. In both cases, the weapon is part of a larger hunting system that integrates keen vision, rapid reflexes, and agile movement. Feathers, too, tell the story of continuity. In Velociraptor's time, they were primarily for insulation, display, and maneuverability, not for flight. In its bird descendants, feathers diversified into a wide array of forms and functions: aerodynamic surfaces for soaring, waterproofing for diving, camouflage for ground nesting, and vibrant displays for courtship. Yet the underlying structure of the feather has remained remarkably unchanged across the ages, a testament to its effectiveness. The beak, a defining feature of modern birds, did not exist in Velociraptor, which retained its toothy grin. But here too there is a connection. Over evolutionary time, teeth were lost in many avian lineages, replaced by lightweight beaks better suited to specialized diets. Some paleontologists suggest that the seeds of this change were already present in small theropods, with gradual reductions in tooth size and changes in jaw structure, paving the way for the beaks we know today. Modern birds also inherit from their dinosaurian ancestors a respiratory system unlike that of mammals. In Velociraptor, as in many theropods, the bones show evidence of air sacs connected to the lungs, a highly efficient breathing system that allows for continuous oxygen flow. This adaptation, perfect for the high energy demands of a predator, was equally advantageous for flight in birds, enabling them to sustain the intense metabolic rates needed for long-distance travel or rapid bursts of speed. Even behavior offers glimpses of continuity. Many ground-nesting birds today guard their eggs with vigilance, shade them with their bodies in the heat, and use displays to ward off intruders. Behaviors that fossil evidence suggests may have been present in dromaeosaurids. The circular arrangement of eggs in some dinosaur nests mirrors the patterns seen in certain modern birds, hinting at a deep-rooted instinct for careful incubation. If we imagine a velociraptor beside a modern bird like a secretary bird of Africa or a roadrunner of the American deserts, the similarities are striking. The long legs built for running, the forward-focused gaze, the calculated strike at prey, all echo across millions of years. The secretary bird even uses its powerful legs to deliver killing blows to snakes, a hunting tactic that may not have been entirely alien to a velociraptor's skill set. The evolutionary journey from feathered dinosaur to modern bird was shaped by the catastrophic extinction event at the end of the Cretaceous. While Velociraptor and most of its larger relatives perished, small-bodied, seed-eating birds managed to survive, possibly because their diets could sustain them when larger prey species disappeared. These survivors spread and diversified in the Paleogene period, filling niches left vacant by extinct species. Over tens of millions of years, this diversification gave rise to the astonishing variety of birds we see today, from hummingbirds to ostriches, penguins to parrots. In this way, every bird alive is a living relic of that ancient world. The pigeon that takes flight from a city street carries in its bones and muscles the same basic plan that powered Velociraptor's leaps. The hawk that wheels in the sky retains the predatory focus and talon strength of its dinosaurian kin. Even the smallest songbird, as it turns its head to study a potential threat, channels the same alertness that once kept a velociraptor alive on the Gobi sands. Understanding this legacy changes the way we see both dinosaurs and birds. It collapses the artificial divide between prehistoric and modern, showing that the age of dinosaurs never truly ended. It simply changed form. For the velociraptor, extinction was absolute, but for its broader lineage, survival meant transformation. The public's growing awareness of this connection has already begun to reshape how dinosaurs are depicted in media and museums. Increasingly, Velociraptor is shown with its full feathered coat, not only to reflect scientific accuracy, but to make the evolutionary link to birds unmistakable. When visitors see the resemblance between the skeleton of a raptor and the frame of a modern bird, the evolutionary story becomes tangible in a way that numbers and charts alone cannot achieve. It also deepens our appreciation for the birds around us. They are not merely delicate creatures of the present, they are the last enduring branch of a once mighty lineage. Each species a survivor of the greatest extinction event in Earth's history. Their songs are the voices of deep time, their flight the echo of ancient leaps, their eyes bright with the same calculating awareness that once scanned the dunes of the Cretaceous. And so in the living world, the velociraptor's spirit persists. It lives in the silent glide of an owl over a moonlit field, in the sudden sprint of a heron striking at a fish, in the fierce talon grip of an eagle on its prey. The names have changed, the forms have shifted, but the essence, the blend of precision, agility, and adaptation remains. The story of Velociraptor is therefore not just a tale of extinction, but of continuity. It reminds us that survival often demands transformation, and that the past is never as distant as it seems. When we watch a bird in flight or see it stalk across the ground, we are not merely observing a creature of today, we are witnessing the culmination of a journey that began long before humans walked the earth, in the shadowed dunes of a desert, ruled by a small feathered predator with a sickle claw and a hunter's gaze. From here, our journey with Velociraptor in this story reaches its end. We have walked its ancient hunting grounds, watched it grow from fragile hatchling to apex desert hunter, seen it face rivals, and traced its legacy into the living skies. Now in the quiet hours it is time to reflect on what it all means before we bid it good night. And so, the Velociraptor slips back into the shadows of history, its story told in bone and stone, in windswept cliffs and delicate imprints of ancient feathers. We have followed it across the parched dunes of the Cretaceous Gobi, through hunts and hardships, rivalries and fleeting moments of triumph. We have watched it face dangers from without and changes from within its world, until the final turning of the age carried it into silence. It was never the monster of myth, nor the unstoppable predator of fiction, but something far more intricate, a small, intelligent hunter, perfectly attuned to the rhythms of its land. Its strength lay not in brute force, but in precision, awareness, and adaptability. These traits shaped its life and, through its close relatives, allowed its legacy to survive even the greatest extinction the Earth has known. Today, its bloodline continues in the birds that fill our skies, sing in our trees, and glide over distant oceans. Every flick of a hawk's wing, every piercing stare of an owl, every quick-footed dash of a roadrunner carries within it a whisper of the Velociraptor's ancient grace. It is a reminder that the past never fully disappears. It transforms, takes on new forms, and endures in ways we might never expect. The Velociraptor's tale is one of survival and change, of the deep connections that bind all life across time. It tells us that even when an era ends, life finds a way to write its next chapter, and in the quiet of the night, when the world slows and imagination roams, we can still walk those ancient dunes in our minds, feel the warm wind of a vanished age, and hear the soft rustle of feathers as a shadowed hunter moves just out of sight. Good night.